Hi, Chem 7. This is the Chapter 9 lecture called Unsaturated Hydrocarbons. So saturated, remember, are alkanes, and they have all single bonds. But unsaturated hydrocarbons have they don't all have single bonds. They can have double bonds and triple bonds. So alkenes are ones that have one or more double bonds. Alkynes are hydrocarbon that has one or more triple bonds, and aromatic hydrocarbons have an aromatic ring. Sometimes that ring is called a benzene ring or an aryl ring, and so we'll have different names for it, but it all means a circular ring of 6 hydrocarbons. So alkenes look like this. They have at least one double bond, and instead of calling them an alkane, we call them an alkene, and then we change the name from 2 carbons as F, and then we call it an ene, so F-ene. So we change the ending to ene to say that there's a double bond somewhere. Propane's the smallest one. It's got 3 carbons, so there's one double bond between the first and second carbon. So like we did the alkanes, we number the carbons from the longest chain. So there's 7 in this longest chain. And then we number them to make the smallest numbers for locations of the beads. We also have to say where this double bond is. So we want smallest numbers for all of the beads and the double bond. So first step is we name the chain, and then we name where that double bond is. So this double bond is on carbon number 1, 2 is on carbon number 3. Then we have to say where the beads are, just like we did before. So this bead, this methyl bead, is on carbon number 2, and this methyl bead is on carbon number 4. So we're going to say 2, 4 is our location, and we have 2 of them, so di, and we have 2 of those methyl groups. Then we say we have a double bond on 3, and it's a heptene because of that double bond. So we'll do these in class. And we can also have, when we have double bonds, we can have geometric isomers. So we can have substituents, those are things that are hooked to that double bond, either on the same side, which is cis. So this is cis because it has 2 H's on the same side. Or we can have trans, where these 2 H's are opposite of each other across this double bond. This has no geometric isomers because we don't have 2 different substituents or things attached to that double bond. We have 3 H's, so we don't have anything unique. We don't have 2 unique things there. So it's in class. Oops, we'll do that one in class. But then if we have a triple bond, we call it an alkyne. So we end the word with YNE. YNE for that. So let's try that one. So this one, we have 3 carbons in a row. We number them, and 3 carbons is a prop. And we have a triple bond, so it's an ine, propine. And we tell you where this triple bond is. It's on carbon number 1. So we try to make that the smallest number for this guy. We also have a bead, a substituent, and that's on carbon number 3. So we're going to say we have a bromo on carbon number 3. So on carbon 3 we have a bromine, and on carbon 1 we have a triple bond. Try that one in class. And so here's what happens with the physical properties. Remember, properties are important for all of these guys, so this is an important slide. So the bigger the molecule, the harder it is to boil, so it takes more and more energy to make it lift from a liquid state into a gas state. So alkynes are different from alkenes and alkanes, so that all of those differences in bonding affect the boiling point. Now, chemical reactions, remember chemical reactivity is the second really important thing to remember on all of these. So it'd be really great if you start making flashcards on the physical properties of each type, alkane, alkene, alkyne, and their chemical properties. So this is an important section right here. Alkenes have three things that can happen. They can either have something added to them, they can oxidize, or they can polymerize. So, addition means you can add things to that double bond and make things bond where you had that double bond. So, if I have a double bond, an alkene, and I add hydrogen to it, and I have a catalyst that helps this happen, I can replace that double bond, with single bonds and have hydrogen up top here. Do the same thing with a double bond and a halogen. That's called halogenation. And I can replace that double bond with putting bromines there. I can also add a water across this alkene. I can put an H on one side and I can put the OH on the other. So I break this water in two. I have a hydrogen catalyst. I put H there and I put an OH there. This is from the water. So I broke the water in two pieces, put one piece there and one piece there. So know these reactions are very important, and we'll be testing a lot on this. Now there's a special rule about how things add to a molecule. It's called the Markovnikov's rule for addition. If you have something that's asymmetrical that you're going to add to a double bond, the carbon of the double bond that has more hydrogens gets the additional hydrogen to it. So I kind of think of it like hydrogens like hydrogens. So if I take that double bond like we talked about just now, I break the water in two pieces, and I see an H there and an OH there, I'm going to look at these two carbons and find the carbon that has more H's on it. So if you look right here, this carbon has two H's, this carbon has one. So H's like H's, so when this H comes off this water, it's going to go where there's more H's. So this H is going to go where this carbon that had two already is going to add one more. So H's like H's, they like to hang up together. And then that OH has to go on this carbon here. So make sure you understand Markovnikov. Every once in a while you'll have a question and you have to put the H in the right place. So make sure you understand that rule. And we'll see it over a bunch of the time. So when we do halogenation, it works, that Markovnikov rule works as well. So here we got a double bond. We look at the two carbons. This one has one H. This carbon has two H's. So where's this H going to go? It's going to go where there's more H's. H's like H's. H goes with H. So this H jumps on here, and the chlorine jumps on to this guy here. So chlorine goes here. Hydrogen goes to this one. That's Markovnikov rule. We'll do practice in class. Oops. Then we'll go to the next thing, which is called oxidation. Oxidation means you're adding oxygen to a bond. So, for example, this double bond in the alkene, if you oxidize it, there's different conditions you need for that, so don't worry about that part. But if you see mild oxidation, you're going to add an OH here to that carbon and an OH to that carbon. So you're going to get rid of the double bond and add an OH and an OH. If that's for mild oxidation. If you really strongly oxidize it with particular reagents, then you can actually break this double bond and break this molecule into pieces. And when you do, you can have oxygen here and oxygen there. So you break this guy in half, put oxygen on this guy and an oxygen on this guy, and that's what happens when you strongly oxidize something. So know the difference between mild and strong oxidation. We can also do polymerization. So polymerization means when you take a small little molecule and you add it to another one of the same kind and you make long, long chains. So we have lots of these little guys, and they're called monomers, and we put a lot of them together and we give them the right conditions, and then they make long chains called a polymer. So each individual unit's called a monomer, and when they combine together, it's called a polymer. So let's talk about the reactions of alkynes. One of them is halogenation. So we're going to take that triple bond, we're going to add chlorine across that triple bond. So you're going to actually add a chlorine here, a chlorine here, a chlorine here, and a chlorine here. So you're going to have chlorines everywhere, and you're going to get rid of the triple bond, and they'll all be single bonds. So this is halogenation. It's called addition, but we're adding a halogen across there. So Markovnikov still comes into play every time we do these things. So we have to look at the carbons that we're going to do the reaction at. And this carbon has no hydrogens on it, but this one has one. So where's the H going to go? It's going to go to this guy that has one. So H is like H's. So this H is going to go on here. This Br is going to go there. So that's what happens. We have H's go on this carbon, and we have the Brs going on to that guy. Aromatic carbons are it's a circle of 6 hydrogens, and it's very, very stable because of the electron cloud. The ring itself is unreactive, but you can have things attached to that ring that are reactive. So here's what the benzene ring looks like. Remember, there's going to be different words that means the same thing. Aryl, benzene, phenyl. There's a lot of different words for it, and we'll talk about those in class. This is a benzene ring. And it has alternating single and double bonds, and this ring structure is super strong, so it's going to be super reactive. So the electron cloud, there's going to be electrons circling around us on the top and on the bottom, and because of that, it makes these rings really, really strong. So we're going to learn how to name these guys. So this ring is called the benzene ring, but sometimes it's called other things, so it can get kind of complicated. When this is the main structure, then we call it a benzene, and then we say, oh, we're adding things to it. So we have a chlorine bead on this benzene ring. But if we decide to name the chain first, then this guy is called a phenyl. So these are kind of complicated to name. And sorry about that, I don't know why they make things so hard. But they named the chain, and then they threw a phenyl group on there on carbon number 3, if you're counting 1, 2, 3. Phenyl on 3, methyl on 2, 1, 2. When we have more than one thing attached to a benzene ring, then we have to give it special names. So if we have one thing attached here, and then we have something attached here, then these guys are called ortho to each other. If it's 2 carbons away, it's called meta. If it's 3 carbons away, it's called para. So I'd prefer that you guys just use numbers, and let's not use the ortho, meta, para, but you might see these in real life, so I wanted you to see and know them. But when we name things in class, we're going to use the numbering system. So I have a chlorine on 1, and I have a chlorine on 3. I have a bromo on 1, and I have a chlorine on 4. Here I have a bromine here, and I have a methyl group. So this guy right here, without the bromine, is called toluene. And then this guy is a bromo. So it's 2-bromotoluene. So that's a common name, so make sure that you've seen this before. I know you might see it in real life, so I want you to see the word toluene. So aromatics are liquids or solids at room temperature. They're very big, and they're nonpolar. They're not soluble in water, but they like things that are like themselves, nonpolar. Toluene's a good solvent, and it will dissolve a lot of hydrocarbons. So that's that methylbenzene. So, because this is super reactive, it will not react with bromine, so nothing's going to happen here. They don't undergo addition reactions. They're not the same as these double and triple bond guys. So, these aromatics will do some reactions, so let's talk about them. For example, if you have benzene, you can attach a methyl group to it and turn it into toluene. So that's called alkylation. We can also add a chlorine to benzene and turn it into chlorobenzene. We can add a nitrate group to it with a catalyst, and we can make nitrobenzene. And we can add a sulfate group to it and turn it into a benzene sulfonic acid. And that's it for this set of slides, so I'll talk to you soon. Have a great day.